Good day, dear colleagues. My name is Irina Nazarova. Today I am representing a group of authors from Donetsk National Technical University and our team's work titled Efficient Parallel Hybrid DIRK Solver for Stiff Complex Critical Infrastructure Models. The aim of this research is to improve the efficiency of modeling large-scale stiff processes of critical infrastructure by combining optimal mathematical schemes with a parallel hybrid approach. Main tasks: development and analysis of parallel numerical schemes of the DIRK family in terms of the efficiency, scalability, etc. Evaluation of the efficiency and convergence of iterative solver for system of nonlinear algebraic equations, development and optimization of direct and hybrid parallelization technologies for scalable mapping to high-perform computing architectures. Execution of an analytical and experimental analysis of the classical Van de Poel benchmark to evaluate the performance and limitation of the proposed approach. Let's start with a brief overview of the related works. The first group of papers, classical analytical works, the theoretical basis for their research. The second group, modern full review for DIRK methods. Next groups, DIRK development, comparative analysis, main actual trend. The fifth group, parallel architecture and computing. Finally, the sixth group, some of the authors' publication on this research topic. To begin with, we will look at mathematical formulation and basic notation of the m-dimensional Cauchy problem for first-order systems of ordinary differential equation. Definition and illustration of a stiff problem. Formal definition of the stiffness number through the eigenvalue of the Jacobian matrix. General representation of the S-stage Runge-Kutta method of ODR in vector form and using the Butcher table. Matrix A and vectors B and C define the unique methods and are selected for convergence and stability consideration. Now, the classification of Runge-Kutta method according to the structure of the Butcher matrix is presented in this diagram. Explicit methods feature a strictly lower triangular matrix A and are unsuitable for stiff problem. Fully implicit methods characterized by a dense matrix A, they are highly stable for computationally expensive. Diagonally implicit methods offer an optimal balance of stability and efficiency, used a lower triangular matrix A with a non-zero made diagonal. Single DIRK methods within the DIRK class use a constant diagonal where all elements equal gamma. And finally, explicit S-DIRK methods within the S-DIRK class feature an explicit first stage, meaning the first row of the matrix A consists entirely of zero. Parallel DIRK methods. Given the limitation of sequential computing in modeling complex COD, exploiting parallel architecture becomes essential. All presented parallel algorithms for DIRK methods were developed using decomposition techniques and influence graph. As you can see from block diagram on slide, the proposed parallel framework is structured into three logical group, methods top group. The general class of parallel DIRK methods is divided into three implementations. Iterative solver middle group shows that each method can be coupled with one of three iterative techniques. Parallel architecture bottom group defines the hardware model, contrasting a poor distributed model using MPI against a hybrid model combining MPI and OpenMP. Our hybrid approach implementing two-level parallelism. At the internode level, MPI handled domain decomposition and data transfer between independent nodes. At the intranode level, OpenMP utilized shared memory to parallelize intensive stage coefficient computation and vector operation. This approach significantly reduced communication and memory overhead, ensuring high scalability for large-scale stiff problem. Comparative analysis of parallel iterative solver. Next, primary computational load of implicit method lie in solving nonlinear system for stage coefficient. We developed parallel algorithms based on three distinct solvers. Fixed point method characterized simplicity of implementation and linear convergence, high risk of convergence loss in stiff modes, inefficiency of stiff problems even in parallel environments. Newton methods, direct classical methods, provides quadratic convergence, high stability for stiff problem, high computational and memory overhead due to the explicit calculation and storage of the Jacobian matrix. Jacobian free Newton-Krylov methods approximate the Jacobian matrix, significantly reducing memory usage and computational cost. Ensure highly scalable parallel computing. Conclusion. For ultra-large-scale problems where explicit Jacobian storage is impossible, Newton-Krylov methods outperforms classical Newton. Summary of performance metrics. In this table we have summarized the key performance or general characteristic, stability, control step size, etc. and scalability metrics of the developed methods. Comparative analysis and conclusion. The parallels as DIRK methods combined with the Newton-Krylov solver offer the highest speedup and parallel scalability under the hybrid MPI plus OpenMP model. Both SDIRK and ESDIRK methods are stable and minimize total overhead in distributed and hybrid models. As the problem size increases, semi-explicit methods successfully compete with and sometimes outperform the DIRK methods in parallel application. Numerical result. Moving forward, the next few slides are devoted to the numerical experiments and a discussion of their result. Testing problem. Van der Pol equation system of M oscillators. This is a classical model in complex cybersecurity system and serves as a standard parallel benchmark. The first experiment group demonstrates the critical influence of the stiffness parameter mu. The second group of experiments demonstrates the dependency on the coupling parameter k. Two extreme bounds are considered: no coupling and strong coupling, representing intensive interaction between processes. The next set of experimental focuses on parallel efficiency metric. Comparison of parallel DIRK, SDIRK and ES methods. We evaluated their speedup, efficiency, communication and total overhead, and the efficiency function to determine how effectively each method scales as problem size increases. Hybrid versus distributed and solver analysis. This slide details the performance of our hybrid approach compared to poor distributed memory. We compared the speed up and efficiency for different number of processor and thread under the hybrid approach, and directly comparing the standard Newton solver with the Newton-Krylov method. Numerical testing of parallel algorithm was carried out on the Hawk supercomputer at the Hillary Supercomputer Center in Stuttgart, as well as in emulation mode. The main finding across all experiments indicates that the hybrid MPI plus OpenMP framework combined with the SDOG scheme and the Newton-Krylov solver delivers the optimal performance. To conclude, scientific novelty, hybrid parallelization model, a new computational model integrating intra-step functional parallelization with spatial decomposition, specifically optimized for SDOG, ESDOG methods, enable efficient modeling of large-scale cyber-physical systems in real time. Optimization of parallel iterative solver, development of analytical adaptive switching mechanism between DIRK Newton and Newton-Krylov solver during the integration process based on real-time monitoring on the system stiffness and coupling density for minimizing total overhead. And advanced complexity modeling, analytical time complexity models for SDOG, ESDOG algorithms that account for multi-level parallelism and iterative convergence rate under dynamic, unpredictable workload. Practical significance. The developed parallel algorithmic and software toolkit provides a robust framework for simulating nonlinear dynamic process within critical infrastructure. Parallel diagonally implicit method combined with adaptable iterative solver enables the software to effectively integrate not only problem of different stiffness, but also those with singularities. The practical viability and computational stability of this approach were validated using classic Van de Poel-Steve benchmark problem, confirming its suitability for modeling system of critical infrastructure and risk reduction. The main direction of future research. GPU acceleration, extending the hybrid MPI plus OpenMP model to heterogeneous CPU-GPU cluster. The investigation of specialized distributed preconditioner, such as Schwartz, within the different topologies for future accelerate the convergence of the Newton-Krylov methods. The integration of the developed parallel algorithm within variable order and variable steps control strategies to optimize computational cost in which the stiffness change dynamically, and the development and study of parallel stabilized explicit Runge-Kutta methods with extended stability region. Thank you for your attention.